Hello, my name is Chen Jiang, and I am a PhD candidate from Auburn University. I'd like to share some work we recently did to incorporate temporal data into a deep learning model in the prediction of the US real estate market. It is well known that economic trends are tricky to predict. Real estate market is no exception. This is a track of the US real estate market history from 1999 to this year. Overall, there is no pattern of the price growth or decline. These major fluctuations may be caused by the big global or national events, like the recession in 2008 and the pandemic year you will see over here. On a smaller scale, you see all these faster fluctuations that can be caused by various reasons, not necessarily restricted to economic factors. All these will increase the difficulties of predicting the real estate market. In addition, the tremendous difficulties of prediction sometimes are due to the lack of history data, and the corresponding supplementary data make it nearly impossible to predict the market for smaller regions. For example, it is very challenging to predict market trends for counties or even neighborhoods. Some early efforts have been made to explore the possibility of using deep learning models to predict the real estate markets. Despite the promising results shown from earlier studies, there are still some limitations that can be greatly improved to enhance the model performance. First of all, most previous studies that use the latest deep learning models have been focused on using datasets from other countries, such as India, China, and Japan. Very limited studies have analyzed domestic datasets. Evaluation of model performance was usually not comprehensively done. For example, to validate the models with most recent local dataset. In the limited set of studies that assess the model accuracy, they were usually not satisfactory enough. Most importantly, for a deep learning model to be able to capture all the possible trends in the market, the dataset we use to train the model should also be able to reflect all the contributing factors to the market fluctuations. The more features a dataset contains, the better performance the model trained with that dataset will likely be. To overcome these limitations, we improved established method and proposed a new way to accurately predict the US real estate market. The first challenge we faced was the lack of domestic dataset. So we compiled a giant dataset of 7,436 neighborhoods, 567 cities, 304 counties, 225 metros, and 50 states across the US. To improve the accuracy and to validate the performance of the prediction model, we encoded the temporal data into the traditional deep learning algorithms and validated the model with the recent dataset from 2017 to 2018. Our model reached about 93.5% accuracy in predicting the US real estate market. One of the reasons that our model performed that well is because we trained the model with a dataset of 294 features that combined temporal features like price history and non-temporal features like location, socioeconomic status in that region. Next, I'm going to show you how our temporal encoding model works. The top of this picture is the conventional structure of a transformer encoder model. We incorporated a dataset full of temporal features down here into the model. Transformer encoder includes a layer that evaluates the hidden relations among the features and a layer that regulated the weighting factors or attention distribution. This part of encoding was only for the temporal features. Therefore, the interior output was calculated based only on the temporal features. Another part of the model was responsible for incorporating the non-temporal features using the ReLU activation function. Then the prediction deep learning network integrated both the temporal interior outputs and the non-temporal features to produce a prediction output. To integrate the interior deep learning outputs of temporal and non-temporal features, we used a classic sigmoid function. The final output was in the form of ranking classifications that reflect the growth rate of the real estate price in each region. The region labeled as class 0 means that the price in this area grows the fastest, and this is the hotspot in the market. In this way, we labeled all the regions in our dataset with a popularity ranking, and the figure done here is just an example of how the rank 0 hotspot spread across the US. To validate our temporal encoding model, we compared the model predicted ranking classification with the ground truth popularity classification of these regions from 2017 to 2018. In different testing conditions, we compared the prediction accuracy when 2, 3, or 5 classes were assumed. The results showed that our model reached an accuracy as high as 93.5% when all data fell into 2 major classes, a rank 0 hotspot and a rank 1 non-hotspot. The accuracy for the other 3 conditions was lower, as you can see in this figure. We further compared our model with other commonly used models in the field with the same dataset. Our simulation showed that our model outperformed all other models in accuracy. Another interesting thing that we found during testing the model is that the non-temporal features are extremely important for improving prediction accuracy. We compared the model accuracy simulated with dataset that only contain temporal features versus dataset that contain both temporal and non-temporal features. And we found that when non-temporal features were not included, basically all models showed decline accuracy. To summarize, in this study, we compiled a new dataset with both temporal and non-temporal features. We proposed to encode temporal data in a transformer model to enhance model performance. We then validated that our model with recent local data, and it showed our model performed really well. Importantly, we demonstrated that the non-temporal features that were normally underestimated by previous studies were of critical value in the prediction of real estate price trends. For future work, we plan to add more non-temporal features such as school district and location specialty to our dataset to improve prediction accuracy. We also plan to test if our model can predict trends under economic crisis, for example, the 2008 economic recession and the recent COVID-19. In addition, we are also interested in using advanced learning algorithms to encode some non-temporal features, for example, to encode location information using graph convolutional network. Lastly, I would like to thank my collaborators and my funding source. Thank you for stopping by and listening. If you have any questions or would like to discuss collaboration possibilities, please feel free to email me. Thank you.